We think we know monsters. We build them in our stories, our movies, our nightmares, but we are wrong. The true monsters were real. They were not lurking in shadows or hiding under beds. They ruled the entire planet, under an open sky, for a staggering stretch of time over 150 million years. And that's a span so vast it makes the entire timeline of human existence look like a single, brief footnote, and then they were gone, vanished, leaving behind nothing but shattered stone and whispers in the rock. This is the greatest detective story ever told. A murder mystery 66 million years cold. The victims are giants, the suspects are celestial, and the clues are hidden in the very ground beneath our feet. This is the hunt for the dinosaurs. Imagine a world where the air is thick and humid, where the continents are locked together in a single, massive landmass called Pangaea, where the forests are made of giant ferns and cycads and the rivers cut through landscapes no human eye would ever see. This is the Mesozoic era, the age of reptiles, and for the longest time, we thought we understood its kings. We pictured them as hulking, slow-moving pea-brained lizards, dragging their tails through the swamp, great big dumb animals waiting for their own inevitable extinction. But here's the shocking truth. That image is almost completely false. It's a fossil of an old idea. And the new picture emerging from the dirt is so much more thrilling, so much more bizarre, and so much more alien than anything we ever imagined. The story of how we know anything at all about these lost rulers begins with a single, remarkable human trait: curiosity. For centuries, people found giant bones. They called them dragon bones, or the remains of biblical giants. It wasn't until the early 1800s, in the quarries of England, that a few sharp-minded scientists began to piece together the puzzle. They realized these were not the bones of oversized elephants or mythical beasts. They were something entirely new, something ancient beyond comprehension. In 1842, the brilliant and eccentric anatomist Sir Richard Owen looked at the fossils of three creatures, Megalosaurus iguanodon and Haleosaurusand, saw a common thread. He saw a distinct, magnificent blueprint of life. He gave them a new name: Dinosauria, terrible lizards. And with that single act of naming, the hunt was formally on. The world had a new category of being to pursue. The late 1800s became the Bone Wars, a frenzied, chaotic, and often ruthless race across the American West. It was a period of high stakes, science fueled by ego, money, and a desperate hunger for fame. Rival paleontologists like Othniel Charles Marsh and Edward Drinkercope used dynamite, spies, bribery, and sheer force of will to pull monstrous skeletons from the painted badlands of Wyoming, Colorado, and Montana. They were discovering creatures so large, so out of scale with anything alive, that they strained public belief and reshaped our understanding of life's possibilities. This was the era that gave us the classic titans that still filled museum halls. The long-necked, pillar-legged Apatosaurus and Brachiosaurus, animals so huge their very bodies seemed like a physics experiment, their hearts possibly weighing over 400 pounds just to pump blood to their distant heads. The spiky Stegosaurus, with a brain the size of a walnut and those mysterious, alternating plates on its back, was still arguing about were they for defense, for display, or for regulating body temperature. And of course the ultimate predator of its time, discovered by Barn and Brown in 1902, Tyrannosaurus rex. Tyrannosaurus, the name alone carries weight. For a century, it has been the undisputed king of the dinosaurs in our imagination, a 40-foot-long 19 embodiment of brute force. We saw it as the solitary, roaring bully of the Cretaceous period, a relic of primitive violence. But modern paleontology has taken this icon and turned it inside out. The discoveries have been mind-blowing. We now know T-Rex wasn't just a blunt instrument. It was a sophisticated hunter, possibly even a social one. Its bones show evidence of brutal face-biting combat with others of its kind, not just for food, but perhaps for territory or mates. Its sense of smell, governed by massive olfactory bulbs in its skull, was probably the most powerful of any land animal ever. The chemical tracking supercomputer in its head, and those infamous tiny arms, they were far from useless. Biomechanical analysis suggests they were incredibly strong, capable of holding on to struggling prey with a vice-like grip, or perhaps even helping it rise from rest. Studies of its inner ear show it had excellent balance and could make precise, rapid movements of its head. This wasn't a slow, lumbering monster. This was an active, intelligent, and terrifyingly efficient predator that may have hunted in family groups. Some of the most fascinating recent finds are of a closely related tyrant, Daspaltosaurus, found in bone beds with multiple individuals of different ages, hinting at complex pack behavior we once thought impossible. But here's the wild part. T-Rex is just one chapter, one branch on an unimaginably dense and weird family tree. The real revolution in dinosaur science isn't about making the old monsters bigger or meaner. It's about discovering that they weren't monsters at all. They were animals. Complex, diverse, and in many ways, surprisingly familiar. The biggest breakthrough of the last 30 years isn't a single skeleton. It's a single idea, supported by an avalanche of stunning evidence. Birds are dinosaurs. Let that sink in. That sparrow at your feeder, the eagle soaring on a thermal, the chicken on your dinner plate, they are not just related to dinosaurs. They are dinosaurs. The direct, living descendants of the small, feathered theropods that once scurried under the feet of giants. This isn't just a theory, it's a fact written in stone. Fossil discoveries, primarily from the exquisite fine-grained lakebed deposits of Leon in China, have shown us dinosaurs covered in feathers, not just fuzzy down, but complex feathers with veins and shafts, feathers for display, for insulation, and for gliding. We have found dinosaurs with wings, with beaks, with colors preserved in the microscopic melanin-containing structures called melanosomes within their feathers. We know that some dinosaurs, like the crow-sized four-winged Machiraptor, had iridescent black feathers that shimmered like a raven's. We know that Velociraptor, the sleek predator made famous by movies, was probably covered in plumage, looking more like a frightening ground-dwelling bird than a scaly lizard, complete with a wishbone. This changes everything. It means many dinosaurs were likely warm-blooded or had some form of elevated metabolism. It means they were active, dynamic creatures that needed insulation to regulate their body heat. It means they communicated with visual signals. They displayed vibrant colors to attract mates or ward off rivals. They lived in complex social groups. We have found evidence of dinosaur nesting grounds, like the vast colony of Maiasaura in Montana, showing parents returning to the same site year after year to care for their young in mud nests. We have found fossils of dinosaurs like Melom, a small troodontid preserved curled up in a roosting sleep position. We have found fossils of dinosaurs fighting, locked in mortal combat like the Velociraptor and Protoceratops found in the Gobi Desert. We have even found a fossil of a Psittacosaurus, a parrot lizard, dying in the act of giving birth. They are no longer just static skeletons in a museum. They are being resurrected as living, breathing creatures with life histories, behaviors, and even personalities we can begin to infer. But if they were so successful, so adaptable, so brilliantly full of life, what happened? How do you kill a world? The answer lies in a single, terrible day. For most of human history, the extinction of the dinosaurs was a slow, mysterious puzzle. Maybe the climate changed gradually. Maybe volcanoes poised in the atmosphere. Maybe mammals ate all their eggs. Then, in 1980, a father-son team of scientists, Luis and Walter Alvarez, proposed a radical theory. What if the end came not from below, but from above? The detective work that followed is a masterpiece of scientific sleuthing, connecting dots across the globe. The key clue was a thin layer of clay, found in Italy, Denmark, New Zealand, and everywhere in between, right at the geological boundary between the Cretaceous and Paleogene periods. This layer, known as the KPG boundary, is rich in iridium, an element rare on Earth's surface but common in asteroids and meteorites. The hypothesis was staggering, a global cataclysm from an asteroid impact. The search for the crater was on. The smoking gun was finally found in the early 1990s, hidden under the jungle in the coastal waters of Mexico's Yucatan Peninsula. The Chicxulub crater, a scar over 110 miles wide, buried under miles of sediment and water. It was made by an asteroid roughly 6 miles across, traveling at something like 45,000 miles per hour. The picture that day, an ordinary morning in the Cretaceous, 66 million years ago. Then, a blinding flash in the sky, brighter than a million suns. The impact released energy billions of times greater than the atomic bomb dropped on Hiroshima. It triggered megatsunamis, thousands of feet high, that scoured coastlines across the Gulf of Mexico. It sent a supersonic shockwave and a hail of superheated debris that incinerated everything for hundreds of miles, creating a wasteland of glass and fire. But that was just the opening act. The real killer was what came after. The impact vaporized carbonate rock, releasing trillions of tons of carbon dioxide and sulfur dioxide into the atmosphere. It hurled billions of tons of dust and soot into the stratosphere. For months, maybe years, the sun was blotted out. Global temperatures plummeted in an impact winter. Photosynthesis ground to a halt. The food chain collapsed from the bottom up. The great forests withered and died. In the oceans, the tiny photosynthetic plankton that formed the base of the marine food web vanished. It wasn't just the dinosaurs that died. It was an estimated 75% of all plant and animal species on Earth. The reign of the terrible lizards was over, ended in the blink of a geological eye by a random rock from deep space. The precision of this discovery is haunting. We can find the minute glass spherules from the impact in the geologic layer. We can trace the soot from global wildfires. This cataclysm, however, created the very conditions for our own story. In the empty, devastated world left behind, small, adaptable, warm-blooded and furry animals, our shrew-like mammalian ancestors, crept out from the shadows of their burrows. They survived on seeds, on insects, on decaying matter, on anything they could find. They inherited a broken world and, over millions of years, slowly, painstakingly rebuilt its biology. Every mammal alive today, From the blue whale to the bat to wasp traces its lineage back to those few tenacious survivors. We owe our very existence, our chance to rise, to that asteroid. It was the ultimate, brutal reset button for the planet. So, where does the science go from here? We are no longer just digging up bones with brushes and picks. We are entering a new golden age of paleontology, powered by technology that sounds like science fiction. We use high-resolution CT scanners to peer inside fossilized skulls without damaging them, digitally mapping the shape and volume of dinosaur brains and inner ears to understand how they moved, what they could hear, and even how they may have processed information. We apply sophisticated synchrotron particle accelerators and mass spectrometers to fossilized bones and eggshells, teasing out isotopic clues about their body temperature, their diet, their migration patterns, and the climate they lived in. We use lasers and a technique called laser-stimulated fluorescence to reveal fantastical details of soft tissue, skin impressions, and feathers completely invisible to the naked eye under normal light. Paleontologists are now as likely to be found in a genetics lab comparing dinosaur protein sequences to birds, or behind a supercomputer running biomechanical simulations, as they are in a dusty desert dig site, and the discoveries are coming faster than ever. Every year, on average, about 50 new dinosaur species are named. We're finding them on every continent, including Antarctica, where species like the armored Antarctopelta prove dinosaurs lived in polar forests. We're discovering entire, previously unknown ecosystems from different time periods, like the prehistoric rainforests of Australia where Australovenator. The future of dinosaur research is dazzling. Imagine using even more advanced particle accelerators to analyze fossils at the atomic level, revealing their original color patterns in stunning, definitive detail across the whole body. Imagine artificial intelligence and machine learning algorithms being trained to scan vast libraries of satellite and geological survey imagery, identifying subtle signatures of potential fossil-rich rock formations from orbit, guiding field teams with unprecedented efficiency. Imagine the possibility, however slim, of recovering longer fragments of original proteins or other complex organic molecules from exceptionally preserved fossils in amber or anoxic mudstones, giving us a direct, chemical window into their biology that could one day hint at physiology and disease. But the most profound prediction is this: our understanding of the dinosaur family tree will keep shifting, branching, and surprising us. The line between what is a dinosaur and what is a bird will continue to blur as we find more and more small, feathered, bird-like dinosaurs. We may have to accept that many of the behaviors we think of as uniquely avian, complex nesting, intricate vocal calls, vibrant mating displays, even the ability to fly were invented by their dinosaur ancestors in stages. We are piecing together the lost world, not as a static diorama of monsters, but as a living, breathing, squawking, and roaring ecosystem of magnificent animals. We stand, then, in a unique and poignant position in Earth's history. We are the first species on this planet capable of looking back, of using reason and tools to reconstruct these magnificent creatures from dust and stone. We are the detectives who solve the mystery of their disappearance. We are the artists who bring them back to life, not with magic, but with the meticulous or inspiring power of science. The dinosaur is a powerful symbol. It represents nature's boundless creativity and its utter indifference. It shows us that biological dominance is always temporary, that catastrophe can come from a clear blue sky, and that life, in the end, is unbelievably, tenaciously resilient, always finding a way through the darkness. So the next time you see a bird take flight, remember, you are not just looking at a bird. You are looking at the end of one world and the fragile, feathery beginning of our own. You are seeing a dinosaur that survived. The giants of bone and scale are gone, but their legacy is written in the stones of the earth and in the very flight of a sparrow. They teach us the deepest lesson the rocks have to offer. The world is inconceivably old. Change is the only constant, and our time here, however grand it may seem to us, is just another brief, brilliant layer in the stone. The age of giants past. Ours, too, will one day be a mystery for some future intelligence to dig up, piece together, and wonder at.